orbit. And there's a good potential that we may be on a descending trajectory and impact the surface of the moon without even knowing it. But then he says, I'll continue to watch it. And we keep working through the communications problems. And in my mind is probably the most difficult decision I'm personally going to make that day. Do we have enough data to continue? Because at the very last moment, headquarters insisted that we don't have a crash recorder on board the lunar modules. So they insisted that our right emission rule, and this was back and forth between headquarters for many days. They wanted a very precise set of conditions where I'd say, okay, we can continue the descent because we have enough data. And I finally got this mission rule written that says, no, it is going to be the judgment of the flight director whether there is sufficient data to continue. So I'm thinking of this, do we have enough data to continue? Yes, yes, yes. So basically my mind is going through that kind of a cycle. And then the crew is making a report where they indicate they feel they're going to be landing long. Well, I got a similar report from my trajectory controller. And basically they indicate that all their trajectory data indicates they're going to be landing also. What we didn't know was that when we undocked the spacecraft, we had not fully depressurized the tunnel. And it was like champagne cork. As soon as we undocked, it was like a very small impulsive maneuver. The spacecraft had performed in over 2 revolutions. As we get ready to go down to the surface, it's moving us further and further and further downrange. Our computers were dumb in those days because it was programmed that we're going to set it down, start down from the right point, and therefore it's going to, if it follows the proper trajectory, it's going to hit the landing point. But now that point that we're starting from has been moved further downrange. About the time I get a call from the Jay Green, my trajectory officer, that says flight radio velocity air is not increasing, I think we're going to make it. Piece of good news. We rotate the spacecraft a bit, a little bit better comm, but it's still broken. It's now coming up to descent -5, where I have to make the go, no go for the landing. Talk with my controllers in there, get their status. I determine we have enough information to continue the descent to the surface of the moon. We give the go for, give the crew the go for our descent. And immediately the communications are all broken, all wiped out. So we don't even know if they got that message. So Mike Collins relays it back down to it one more time. We get the confirmation from the crew. They understand their go for power descent. So basically we're watching. Communications is slowly getting better. The crew reports a minor electrical problem. My controllers indicate that we don't have any problems with AC voltage on board the spacecraft. Now get down to the time of engine start. And it's very important for us to capture that engine start data because all the propellants that have been loaded at the pad, we need to verify that there's been no leaks, no other problems in the spacecraft. So what we want to do, as soon as the spacecraft gets under acceleration, we can now get a very precise measurement of all the propellants loaded in the spacecraft. That doesn't happen because we lose data right at the time we need to get that. But now the crew is starting to move down towards the surface. And for the first couple minutes, it proceeds very well. We're looking for the landing radar data to come in because the best knowledge that we have, the potential air potential we have on the ground when we load the LEM guidance computer is about 3,000 foot altitude. Well, that isn't good when you're trying to go down to the moon. Because if you're not careful, you'll drill a hole and you'll be 3,000 feet below the surface of the moon. So we have to use the LEM guidance radar. Basically a landing radar to update our knowledge of the altitude. So we're waiting for it to come in, we're waiting for it to come in, we're waiting for it to come in. And then we get a call, 1201 alarm. And there's a real pause in all communications. Every controller recognizes that particular alarm from a training run we had, the final training run before we sent the crew to the Cape, and we blew it on our final training session. But now we know what to do. We're looking at the characteristics of that 1201. Are we seeing any aberrations from a standpoint of the performance of the spacecraft? Are we still firing the jets properly? Are we still performing maneuvers? Is the computer still being updated on board the spacecraft. So we give the crew a go on that alarm. Now what is important, there's two types of alarms we have, what we call a bailout alarm, which is the one we just saw, which basically indicates the computer's running out of CPU time. And what it has to do, it resorts to a priority scheme where it's servicing only the most important things. If we have a sustained run of these bailout alarms, it'll go into what we call PUDU, Root Program 00. And if that happens, the mission's over. So what we must do is we must leap into the fray and tell the crew to stop calling up certain displays. We're going to provide them altitude information, etc. And we continue on down. As we move towards the surface now, we recognize we're going to be much longer than we had expected. We're up near the total footprint. Communications have dramatically improved by now as the spacecraft pitched overhead. We've got a good look angle at the antennas. We now get down close to the surface, and as we get towards the bottom of the fuel tank, we have what we call a low-level sensor. Low-level sensor is like driving in your automobile when it's reading empty. In the lunar module, once we hit this point in the tank, hemispherical, we no longer can measure it. But we know empirically from the volume that's down there, we will have 120 seconds of fuel remaining at an average throttle setting of 30%. Once we hit low level, I have one of my controllers in the back room who has two stopwatches. And he has an analog recorder in front of him that is looking at a single trace. Throttle percentage above 30% and the throttle percent below 30%. And every time it goes above 30%, he starts a stopwatch going. When it comes down, he stops one because now we're going below 30% throttle, and he starts the other stopwatch. And he's mentally subtracting these two stopwatches every 10 seconds and providing a voice call into the control room. The voice calls come into Bob Carlton, who's my lunar control engineer, and you start hearing 120 seconds, low level. Then you hear 90 seconds, then you hear 60 seconds, then you hear 45 seconds, then you hear 30 seconds. And the crew isn't anywhere near the surface yet. They give the call, they're picking up some dust, they can see a shadow. But you can see that he's really moving around the surface of the moon very rapidly, trying to find a suitable landing spot. About the time that Carlton says fifth, we recognize the crew is going through engine shutdown. They have just landed on the surface. And it's an incredible time because the people in the viewing room behind us, it's the only thing we were never trained for, start stomping their feet on the ground. They start applauding, they start cheering right on the line, but we got to hold it all in because in the next 2 minutes we have to go through a stay, no stay decision. So we suck it back up while the world's celebrating. We're looking at that spacecraft very carefully to make sure that it's safe to remain on the surface for the next 2 minutes. And once we finish that, we're still not through. Now we got to go through a stay, no stay decision for 8 minutes. We look again at the spacecraft in more detail. The team's hanging in there real tight. We give the crew the go for the 8 minutes stay, no stay. Then we have one again at 2 hours. And finally, after 2 hours, this team can finally take a deep breath and recognize that we've just landed on the moon. It was a marvelous time because, again, these young controllers hung together. Split-second decisions, absolute decision, absolute discipline in every call they were making. They not only looked after their business when one of the controllers next to them needed help, they'd help him out. So we then milled around for a period of time. The original planning was for the crew to go to sleep. Nobody believed the crew would go to sleep right after landing in the moon. So we had another team in place who was, if the crew decided to go EVA, that we'd get on with EVA. Apollo 12 was a challenge. It was a challenge right at the very beginning because as we left the launch pad, we were hit twice by lightning. We had 3 crewmen in rounding up towards orbit, and the only thing working was booster propulsion and booster guidance. Mission control had 2 minutes to save that mission. But voiced the instructions up to the crew to throw a very obscure switch that would restore part of our telemetry. With telemetry online, the team could get to work, verified reactants were flowing into the fuel cells, brought the fuel cells back online, secured the power system. Everything kept working, got the crew up into orbit. Delayed injection to the moon by 1 rev so we could check the spacecraft out as completely as possible. None of a very gutsy move, we decided that we'd go for it. Apollo 13, you all know the story. It was much more complex than ever depicted in the movie. Key decisions were which way we're going to come back. We could go around the front side of the moon, the back side of the moon, go completely around the moon. We had no data to do it. It was my call. It was pure gut decision. Once we made that decision, that set everything else from a standpoint of power profile that we'd have to perform. As a result of the explosion, there was debris clouds surrounding the spacecraft, so we had to figure out new ways to navigate using Sun, Earth, and the Moon because we couldn't see our navigation stars anymore. We had to come up with a get home fast maneuver to bring us home essentially a day earlier. And to do this, we used the engine that we would have landed the moon to increase our forward velocity by roughly about 1,000 feet per second to cut a day off the return journey. Once we got through that, we could power down the spacecraft. We brought it down to a level that basically turned it into a refrigerator. We were worried about survival of the crew, survival of the systems. To basically try to warm up the spacecraft as best as possible. We had done a barbecue type maneuver to spin the spacecraft perfectly on its axis so the sun could eat all sides. We'd never done before. We got that done. Then we had to, and you've seen this well depicted in the movie, crew suffocating. We've run out of the chemical scrubbers we use, and the spacecraft contains lithium hydroxide to remove the carbon dioxide from the air from the crew's breathing. So we had to invite the devices to fit the square scrubbers and the dead command module into the round holes in the lunar module. And then when we had finished that, we found out that we're not on the proper trajectory back home, so we have to invent a way to perform a maneuver without any computer. So we tell the crew to look out the triangular windows of the lunar module and basically sight in on the Earth. He's got a telescope type device that we use. And basically we use the Earth as a reference, and actually we use their terminator as a reference. This position the engine properly so it could correct the trajectory. And then in order to control it, we said to Jim Lovell, Jim, when the engine starts, you keep the Earth from moving up and down. Fred Hayes, you keep the Earth from moving left to right to your controller. Put 14 seconds into your wristwatch. And doggone if that didn't work. We finally got that done. Then we had to invent a 500 part checklist for the crew to use during reentry, so we basically leave the spacecraft oriented and the attitude needed to explosively separate the pieces. And then this checklist worked out very late in the mission. We found out as the crew was getting just about a couple hours from reentry. We were off our reentry trajectory. We had to perform an emergency maneuver which messed up our power profiles, which caused us to lose a battery when we were on the main parachute. When we hit the water, we had less than 27 minutes of power. So that was Apollo 13. 14 was interesting for all you computer types. We were going around the front side of the moon in the very last pass that we had. And one of my controllers looks up and he sees the abort light on his console. And he knows that there's no check of the abort system, and that if the engine had been armed, this would have been catastrophic. So he immediately no-goes the landing, talks to his backroom pipe. They feel they got a solder ball in the abort switch up there, so they have the crew racked on the instrument panel by the abort switch, and doggone it, the abort indication goes away. So now they say we got 2 hours to save this mission. So they come up with the idea that if I can get the engine started without triggering an abort, the solder ball will migrate to a different spot on the switch and it'll remain there as long as we remain under acceleration. So in 2 hours we wrote a software patch to allow us to start the engine without triggering the abort. Once we saw that the solder ball had migrated away from the abort switch, We then had another software patch to re-enable all the stuff that we just disabled. The crew had never seen it, and this allowed Ed Mitchell and Alan Shepard to get to the surface of the moon. Apollo 15 was an interesting one. We learned the absolute limits of human performance. This is our first mission with 3 EVAs on the surface of the moon. Crew finishes their final EVA totally dehydrated. Dehydrated to the point where blood chemistry has changed. They're deficient in blood potassium, which regulates cardiac function, causes other problems. So on the surface of the moon, we're seeing cardiac problems, runs of PVCs and Jim Irwin. As we get into power flight, we're now seeing the same thing in both crew. This also leads into such things as memory lapses and a few of the other things. So now we're working, trying to get these crew up into orbit. Get the equipment transferred into the lunar module, get ready and separate. So we have found that one. Apollo 16, we had to work around the steering engine problem in order to allow the spacecraft to separate. 17 was about the only normal mission we had. But for us, this was a marvelous time to live because we believed in this dream that were given by John F. Kennedy. We considered ourselves privileged and proud to be part of this brotherhood that formed in the early years of spaceflight. We thank our country every day that gave us a chance to participate in this great adventure. So this is just one of the stories in Mission Control. This room has many stories. It has the stories of the teams deploying for Skylab. All of a sudden, we're moving from an 11-day max mission up to basically a mission that spans the entire year. So you learn a lot about spacecraft. You essentially rewrite the books on the business of flying and all the procedures you use. You move into the Soyuz program. You have to learn to deal with the Russians. You move into the shuttle program. Shuttle was a real challenge for me and for many of the teams because many of the people that we had through Mercury, Gemini, Skylab, and then Soyuz were now retiring. So we had to bring in entirely new teams of young people. Again, just like yourselves, we had to bring them up into this business of mission control. We had to establish the culture, the basic set of values that we hang on to when times get tight. And now we're going through another departure. The shuttle program will be diminishing. We'll be shutting it down within a year. And then it's on back to the moon and Mars. And again, it is my hope that some of you folks will be there the day we go back to the moon and we once again land and we plant the American flag there. And you feel the same pride, the same emotion, the same satisfaction at meeting this challenge of bringing our nation back into the business of exploration, the business of inspiring the generation that will follow you to take up the difficult subjects, engineering, math, science, accept the challenges, to be somewhat different in this somewhat materialistic world. So I congratulate you on just being here, and I hope that some of you will find yourself 5, 8, 10 years from now in a place called Mission Control, sitting in console as flight director. Thank you.